Imagine standing on a quiet hilltop at night, looking up at the sky. The stars seem countless, sparkling in precise patterns across the vast darkness. It feels like the universe is orderly, almost deliberate, as if it follows rules that are invisible yet absolute. Now consider something remarkable. The rules that govern the cosmos, gravity, motion, the behavior of light, even the tiny particles that make up matter, all follow patterns that humans can describe using mathematics. But here's the puzzle: mathematics, as we know it, is a human invention. Numbers, equations, and abstract concepts were created in our minds to organize our thoughts, solve problems, and make sense of the world around us. Yet somehow, these human constructs perfectly describe a universe that existed long before we were born. How can it be that ideas we invented match the behavior of stars, atoms, and energy so precisely? Consider a simple example: counting. Humans created the numbers 1, 2, 3, and so on. Initially, they were symbols for grouping objects. 2 apples, 3 stones. They were entirely our creation. But the rules of arithmetic, which seemed like a convenient invention, suddenly predict the outcomes of real-world events. 2 apples plus 3 apples equals 5 apples, not because nature is compelled to obey it, but because the underlying reality of discrete objects aligns with the abstract system we devised. Extend this to physics, and the coincidence becomes extraordinary. Newton formulated his laws of motion centuries ago using concepts and symbols he created. Yet these equations precisely describe the orbits of planets and the trajectories of projectiles. Even today, we can predict eclipses hundreds of years into the future using mathematics that Newton developed before anyone had imagined modern technology. Mathematics is not limited to simple counting. Humans created concepts like calculus, designed to understand change in motion, long before we had any reason to predict planetary motion or rocket trajectories. Yet calculus allows us to launch satellites into orbit, navigate spacecraft, and even predict the path of comets. We invented the tools, but the universe responded to them. Consider another example: imaginary numbers, which were initially thought to be useless because they did not correspond to anything tangible. Today, they are essential in understanding electricity, quantum mechanics, and waves of all kinds. Something we created in thought finds its reflection in the deepest structures of reality. This is where the mystery deepens. It is one thing for mathematics to approximate reality as a map approximates a landscape. It is quite another for it to predict and explain the universe so precisely that we can foresee phenomena we have not yet observed. This raises profound questions about the relationship between human thought and the universe itself. Are we discovering universal truths that exist independently of our minds, or are we imposing structures on reality because our brains are wired to perceive patterns in the world? Feynman often marveled at this. He would emphasize that no one understands why mathematics works so well, but the fact that it does is one of the most astonishing features of our reality. Even everyday experiences demonstrate this alignment between human, invented math and reality. Waves in the ocean, for instance, behave according to sine and cosine functions, which humans formulated on paper long after waves existed. Light reflects, refracts, and interferes according to mathematical principles that were entirely developed in human thought. Probability, a concept born to describe uncertainty, perfectly predicts radioactive decay, genetic variation, and even chaotic systems. Across scales from subatomic particles to galactic structures, the universe responds to mathematical descriptions invented by the human mind. The deeper one thinks about it, the more astonishing it becomes. We create abstract systems, symbols, and equations for understanding. Those inventions do not merely help us interpret reality. They align with reality at a level that is precise, universal, and often unexpected. The tools we design in our imaginations allow us to predict events long before they occur, to manipulate matter with extraordinary precision, and to comprehend the cosmos itself. The fact that mathematics, something entirely born from thought, corresponds so perfectly to the universe is not just remarkable. It is a profound mystery that continues to challenge and inspire scientists, philosophers, and thinkers alike. Let's explore this mystery further. Mathematics, while invented by humans, does more than describe the world superficially. It penetrates the very core of reality, revealing patterns and structures that exist whether we observe them or not. Consider the planets. Long before humans could travel to space, ancient astronomers noticed the movement of celestial bodies. They could track the motion of planets and stars, but it was mathematics that allowed them to make sense of these patterns by creating concepts like geometry, ratios, and eventually calculus. Humans could predict eclipses, retrograde motion, and the paths of comets. The universe followed rules that were entirely consistent with the frameworks we devised. These rules existed independently of human thought, yet they could be captured, described, and predicted by ideas born in the human mind. This alignment is not limited to celestial mechanics. Take electricity and magnetism, for example. In the early 19th century, humans were just beginning to understand the invisible forces that made magnets stick and wires conduct. James Clerk Maxwell developed a set of equations describing electric and magnetic fields, purely mathematical constructs at first. These equations predicted the existence of electromagnetic waves long before anyone had detected radio signals. Today, they form the foundation of virtually all modern communication: radio, television, internet, and satellite signals. The mathematics we invented describes reality with astonishing precision, often anticipating discoveries decades or even centuries ahead of observation. Another striking example lies in quantum mechanics. Early in the 20th century, the behavior of electrons and photons seemed bizarre, unpredictable, and counterintuitive. Yet the abstract mathematical framework developed by scientists like Schrödinger and Heisenberg predicted outcomes with incredible accuracy. Electrons behave like both particles and waves, yet the equations describe their behavior perfectly. It's as if reality itself is written in the language of math, waiting to be discovered. The strange duality of particles, superposition, and entanglement. All of these would be meaningless without the equations humans created to understand them. Feynman often used analogies to help explain this phenomenon. He would describe a bird in flight. The bird does not think about aerodynamics, yet its wings obey physical laws. Similarly, the universe does not know our mathematics, yet the patterns we observe can be expressed precisely through symbols, formulas, and theorems we invented. Imagine writing a recipe for something that already exists perfectly. You might refine the recipe over time, discovering the exact ingredients and proportions that nature had been following all along. Mathematics functions like that recipe. It captures the universe's underlying logic and allows us to interact with it in predictable ways. Probability offers another lens. Humans created mathematical rules for chance and uncertainty. Initially, probability was used to understand games of chance, like dice rolls or card draws. Yet probability perfectly predicts radioactive decay, genetic mutation rates, and the behavior of large ensembles of particles. It applies to systems far beyond human intuition. Something as abstract as chance mathematics aligns with events happening billions of times across the universe, as if reality itself conforms to the structures we imagine. The implications are staggering. Mathematics is not simply a tool. It is a bridge between human thought and the universe. It allows us to see patterns invisible to the eye, to manipulate matter, and to predict the behavior of systems from the microscopic to the cosmic scale. The fact that human-invented ideas describe reality with such precision challenges our understanding of what it means to discover versus invent. It raises questions about the deep relationship between the human mind and the cosmos, questions that Feynman himself delighted in exploring. The mystery deepens when we consider areas of mathematics that were developed with no practical purpose in mind, yet later prove essential for understanding the universe. Consider imaginary numbers. For centuries, mathematicians considered the square root of -1 to be purely abstract, an invention with no real-world counterpart. It seemed like a mathematical curiosity, a strange anomaly that existed only on paper. Yet today, imaginary numbers are indispensable in physics and engineering. They describe alternating current in electrical circuits, the behavior of quantum particles, and the propagation of waves. A concept invented for theoretical reasons suddenly becomes the key to unlocking fundamental truths about reality. This illustrates a remarkable pattern. Human creativity in mathematics anticipates natural phenomena that we have not yet observed. Even more striking is the idea of non-Euclidean geometries. For thousands of years, geometry was based on Euclid's postulates, describing flat space and simple angles. Mathematicians eventually explored alternative geometries, where parallel lines could diverge or converge, and the rules of shapes behave differently. Initially, this was purely abstract reasoning, with no application in the real world. But when Einstein developed his theory of general relativity, the curvature of space-time around massive objects was described using precisely the non-Euclidean geometries mathematicians had invented centuries before. Human imagination created a framework that the universe was already following, perfectly matching a reality that existed long before we understood it. The predictive power of mathematics in describing reality is not limited to physics. In biology, mathematical models created for entirely different purposes can describe the spread of diseases, the structure of populations, and the behavior of ecosystems. Population dynamics, modeled with differential equations invented by humans, predict the rise and fall of species, the interactions between predators and prey, and even the stability of entire ecological systems. These are patterns that exist independently of human thought. Yet our mathematical inventions capture them precisely. It is as if by thinking abstractly, we tap into a universal logic that the universe itself obeys. This phenomenon raises profound philosophical questions. Are we discovering patterns that exist independently, or does our brain, shaped by evolution to survive in the physical world, naturally construct mathematical frameworks that align with reality? Perhaps mathematics is both invention and discovery, invented as a tool to organize experience, yet discovered as a reflection of deep truths embedded in the universe. The more we explore, the more it seems that the universe is inherently logical, structured, and comprehensible through the language of mathematics. Yet this comprehensibility is not guaranteed. If reality were only slightly different, our equations might fail entirely. The fact that mathematics works is not just convenient, it is remarkable. Another illustration comes from quantum mechanics. Schrödinger's equation, an entirely abstract construction, predicts the probabilities of particles' behavior with astonishing accuracy. Feynman himself developed techniques, like the path integral formulation, that rely entirely on mathematical reasoning. These methods allow us to calculate outcomes in systems that cannot be observed directly. Particles behave in ways that defy intuition. Yet mathematics provides a precise description of their behavior. Reality unfolds exactly as the equations predict, even in domains that seem entirely removed from everyday experience. Ultimately, what is striking is the universality of mathematics. It applies across scales, across systems, across phenomena. Numbers and equations invented in human thought, often abstract and hypothetical, consistently reveal the hidden structure of the universe. From the movement of galaxies to the oscillation of atoms, mathematics bridges the gap between human imagination and cosmic reality. The question remains, why does this bridge exist at all? Why does our invented system align so perfectly with the independent workings of the cosmos? This mystery continues to fascinate scientists and philosophers alike, hinting at a profound connection between the mind and the universe that defies simple explanation. The deeper one looks into the relationship between mathematics and reality, the more astonishing the alignment becomes. Consider probability, a branch of mathematics initially invented to understand games of chance, like rolling dice or drawing cards. It was abstract, theoretical, and entirely human devised. Yet probability now predicts phenomena across the universe, from radioactive decay to genetic variation, and even the behavior of complex systems like weather patterns and financial markets. A concept invented to describe uncertainty in human activity turns out to be a universal tool, accurately modeling events that unfold without any awareness of human thought. This suggests a profound truth. The patterns we see in mathematics are not merely convenient tools, they reflect structures inherent to the universe itself. Take the example of waves. Humans created sine and cosine functions to describe oscillations and patterns. At first, these functions were abstract representations on paper, useful for understanding harmonic motion or for solving mathematical problems. When scientists applied these functions to the physical world, they found that they perfectly describe sound waves, light waves, and even the quantum waves that govern subatomic particles. A concept that began as a mental abstraction maps flawlessly onto phenomena that exist independently, as if the universe had been written in the language of mathematics all along. Mathematics also allows for prediction beyond what is immediately observable. Astronomers using mathematical models can predict the position of planets centuries into the future. Physicists can calculate the energy levels of electrons and atoms with incredible precision. Engineers can design bridges, airplanes, and spacecraft using equations developed long before these structures were built. The predictive power of mathematics is unparalleled, providing insights into systems that humans could never intuitively understand. This predictive ability raises an extraordinary question. Why should something invented in human thought anticipate the behavior of an external, independent universe so perfectly? One way to approach this mystery is to consider the universality of physical laws. The same mathematics that describes planetary motion on Earth applies to distant stars and galaxies. The equations governing quantum particles on our planet also apply to the particles in the farthest reaches of the cosmos. These consistent patterns suggest that the universe operates according to underlying structures that are, in some sense, inherently mathematical. Humans did not create these structures. They discovered a framework that already existed. Yet, the act of discovery requires invention. We had to create the concepts, symbols, and techniques that allow us to recognize these patterns. The alignment between human mathematics and universal reality is particularly striking in areas where intuition fails. Quantum mechanics and relativity describe realms that are completely counterintuitive. Particles exist in multiple states simultaneously. Time stretches near massive objects and space can bend. Our everyday experiences offer no guide to these phenomena, yet the mathematics predicts their behavior exactly. It is as though the universe is constructed according to rules that are accessible only through abstract reasoning, not through sensory experience. This interplay between invention and discovery challenges our understanding of both mathematics and reality. We invent tools, symbols, and methods to explore the world. Yet these inventions reveal structures that preexist our thinking. Mathematics is not a mere language. It is a lens through which the universe becomes intelligible. Every equation that accurately models the cosmos is a testament to this profound connection. Feynman often marveled at this mystery, emphasizing that the effectiveness of mathematics is one of the deepest, most remarkable features of the universe. The human mind, through abstract thought, is capable of uncovering the rules that govern reality itself, bridging the gap between imagination and existence in a way that is both extraordinary and humbling. As we explore the connection between mathematics and reality, the role of abstraction becomes even more remarkable. Humans create mathematical concepts as tools to organize, measure, and predict. These concepts start as purely mental constructs, yet when applied to the physical world, they often provide precise and reliable descriptions of phenomena we could never have imagined. Take, for example, differential equations. These were developed to describe rates of change and motion in abstract problems. Later, they became essential for modeling everything from planetary orbits to fluid dynamics and population growth. A method invented on paper finds its reflection in reality, revealing patterns that existed long before humans ever thought to describe them. Consider physics, where mathematics serves as a bridge between thought and observation. Equations describing forces, energy, and momentum allow scientists to predict outcomes in experiments before performing them. Launching a spacecraft, predicting chemical reactions, or even designing modern electronics relies on formulas humans devised, yet these formulas correspond perfectly to reality. It is astonishing that a system of symbols, purely invented in human minds, can so accurately describe a universe that existed billions of years before our species emerged. Feynman often pointed out that this effectiveness is not something we fully understand, yet it is one of the most profound aspects of science. Another striking example lies in the application of abstract mathematics to quantum mechanics. When Schrödinger formulated his famous equation, it was a product of imagination and reasoning, constructed to represent probabilities in a mathematical framework. At the time, no one could directly observe electrons behaving in the ways predicted by these equations. Yet experiments confirmed that the abstract mathematics was correct, predicting behaviors that defied human intuition. Particles acted in ways that seemed impossible, yet the equations guided scientists to precise understanding. Imagined concepts, when applied rigorously, describe aspects of the universe that are entirely beyond our sensory experience. Mathematics also allows humans to see connections between phenomena that appear unrelated. Complex numbers, once considered purely imaginary, reveal their power in describing waves, oscillations, and electrical circuits. Calculus, initially developed to understand motion and change, underpins modern physics, engineering, and even economics. The structures humans create in their minds often turn out to be the universal language of reality itself. It is as if the universe is already written in a mathematical code, and our task is to decipher it using the tools of invention and logic. This deep alignment between thought and reality raises profound questions. Are humans discovering something pre-existing, or are we imposing patterns on an otherwise indifferent universe? Perhaps the answer lies somewhere in between. The universe exhibits patterns, regularities, and symmetries, and human intelligence evolved to recognize and formalize these patterns through mathematics. Our inventions reflect both the external order of reality and the internal structures of human cognition. The effectiveness of mathematics is not guaranteed. It is remarkable, almost miraculous, that human-created ideas can so accurately describe the independent workings of nature. Through mathematics, we can predict, understand, and manipulate the world in ways that seem almost magical. The abstract concepts we devise illuminate the hidden order of the cosmos, allowing us to glimpse the structure of reality itself. The universe is not chaotic or random. It obeys laws that are discoverable, expressible, and astonishingly precise. Feynman would remind us that this is not simply convenient, it is deeply mysterious. The fact that human invention and cosmic reality align so perfectly challenges us to think about the mind, the universe, and the profound connection that links them in ways we are only beginning to comprehend. The connection between mathematics and reality becomes even more striking when we examine phenomena that initially seemed completely counterintuitive or abstract. Consider relativity. When Einstein proposed that space and time are not fixed but flexible, bending in response to mass and energy, it defied everyday human experience. Time dilation, length contraction, and the warping of space were concepts almost impossible to imagine. Yet the mathematics he developed predicted these effects with incredible accuracy. Experiments have confirmed them repeatedly, from the behavior of GPS satellites to the observation of light bending around massive stars. Mathematics, a system entirely created by humans, perfectly captures the behavior of the universe in ways our senses cannot perceive directly. Another compelling example is chaos theory. Mathematicians developed equations to describe complex dynamic systems, often as exercises in abstraction. Later, these same equations were used to model weather patterns, population dynamics, and fluid turbulence. Tiny differences in initial conditions lead to dramatically different outcomes, yet the mathematics reliably describes the system's overall behavior. Human invention and abstract thought predicts real-world phenomena with startling precision. The fact that such abstract tools can map chaotic systems, which seem entirely unpredictable at first glance, highlights the profound effectiveness of mathematics. Quantum mechanics further deepens the mystery. When physicists like Heisenberg and Schrödinger formulated their equations, the behavior of particles seemed bizarre, defying intuition. Electrons exist as probabilities, not fixed points. Particles can interfere with themselves, and outcomes often appear random yet obey precise statistical patterns. The mathematics developed to describe these behaviors does more than model them. It predicts experimental results that would otherwise be impossible to anticipate. Human-created symbols and equations describe the fundamental structure of reality at scales far smaller than anything we can see. It is as though the universe itself is written in mathematical language, and our task is to learn the alphabet. This effectiveness raises profound questions about the nature of discovery and invention. Humans invent mathematical frameworks, yet these frameworks uncover truths that exist independently. It is almost as if mathematics is both a creation of the mind and a mirror of reality. The abstract structures we devise, the numbers, functions, and theorems, are reflections of patterns already embedded in the cosmos. Consider symmetry. Humans formalized symmetry in group theory and abstract algebra, yet these ideas describe everything from crystal structures to particle interactions. Concepts thought to exist only in theory become indispensable for understanding reality. Feynman often emphasized that this is not something to take for granted. The fact that human thought aligns so precisely with the universe is astonishing. It is not merely that mathematics is useful, it works on a fundamental level. It allows humans to predict, manipulate, and comprehend reality in ways that seem almost miraculous. Our inventions in thought provide a lens to see the underlying order of nature, even in areas far removed from immediate physical observation. Mathematics proves its power. Topology, abstract spaces, and multidimensional mathematics, developed for purely theoretical purposes, now inform advanced physics. From from string theory to cosmology. Equations created in the mind describe the behavior of objects and forces billions of light years away or at scales far smaller than an atom. The predictive and explanatory power of mathematics is universal, spanning the vast scales of reality. Ultimately, the relationship between invented mathematics and the structure of the universe suggests a profound connection between human cognition and the cosmos. Mathematics is not merely a tool, it is the key to understanding existence itself. It bridges imagination and reality, turning abstract thought into a mirror of the natural world. The fact that our invented concepts describe the universe so precisely is both humbling and awe-inspiring, revealing that the human mind is capable of accessing truths that are astonishingly deep, universal, and enduring. The profound connection between mathematics and reality reaches its most astonishing depths when we consider the universe as a whole, from the tiniest particles to the largest cosmic structures. Mathematics created in human thought applies not just locally but universally. The equations that govern the motion of an electron in a laboratory also describe the behavior of stars and galaxies billions of light years away. Concepts developed purely in abstraction, such as calculus, complex numbers, or non-Euclidean geometry, suddenly become the tools that unlock the mysteries of the cosmos. It is not merely that mathematics is convenient, it is that it works at every scale, from the subatomic to the galactic, in ways that consistently align with reality. This universality is both humbling and awe-inspiring. Consider cosmology, the study of the universe as a whole. Mathematical models allow scientists to predict the expansion of space, the behavior of galaxies, and even the cosmic microwave background radiation, remnants of the Big Bang. These predictions were made decades before some of the phenomena were directly observed. The mathematics developed was not a response to these observations, but a tool that anticipated them. Equations written on paper, devised through human ingenuity, describe processes that existed long before humans evolved. The predictive power of mathematics suggests that reality is structured in ways that are inherently comprehensible, even if our senses cannot perceive them directly. Quantum mechanics provides another striking example. Particles at the smallest scales behave in ways that defy classical logic. Electrons do not have definite positions until measured, and light exhibits both wave-like and particle-like behavior. Despite the strangeness, the mathematical frameworks developed by physicists accurately predict the outcomes of experiments every time. Schrödinger's wave equation, Heisenberg's matrix mechanics, and Feynman's path integrals all describe behaviors that are counterintuitive yet real. These tools, born from abstract reasoning, reveal that even at the most fundamental levels, the universe operates according to patterns that can be expressed mathematically. The effectiveness of mathematics also highlights an intriguing philosophical question. Are we inventing math or discovering it? While humans create the symbols, rules, and structures, these creations align so precisely with reality that it seems they were waiting to be discovered. Imaginary numbers, initially thought to be meaningless, describe wave functions in electrical circuits. Abstract geometries created without practical application predict the curvature of space-time. Probability, developed for games and theoretical exercises, describes natural processes from radioactive decay to population genetics. These examples show that our inventions are not arbitrary. They tap into an underlying structure of realities. Feynman often emphasized that this is not a trivial observation. The alignment between human thought and universal behavior is a profound feature of existence. It is as if the universe has a logic, a structure that can be accessed through thought and reason. Human creativity allows us to construct frameworks capable of describing phenomena we cannot directly perceive. Each equation, theorem, and model serves as a bridge, connecting imagination to reality, thought to observation. This connection suggests a remarkable conclusion about the nature of knowledge. The universe is not chaotic, random, or unknowable. It obeys laws that are discoverable, comprehensible, and consistent. Mathematics is the language through which these laws are revealed. By inventing mathematical tools, humans gain access to the underlying structure of reality. Our minds, through abstraction, can glimpse the cosmos itself. The fact that a system invented in thought can describe a universe that existed long before humans ever appeared is nothing short of extraordinary. It challenges us to reconsider the boundaries between creation and discovery, between mind and cosmos, and it inspires a sense of awe at the elegant, mysterious order of existence. The profound relationship between mathematics and the universe becomes even more striking when we consider its role in understanding the fundamental forces and structures that govern reality. Gravity, electromagnetism, the strong and weak nuclear forces, all of these are described through mathematical equations. Newton's law of universal gravitation, formulated centuries ago, predicts the motion of planets and moons with extraordinary accuracy. Maxwell's equations, developed in the 19th century to describe electricity and magnetism, not only explained known phenomena, but also predicted the existence of electromagnetic waves, paving the way for technologies like radio, television, and Wi-Fi. In each case, human invented mathematical frameworks, revealed patterns in nature that were previously hidden, enabling us to comprehend and manipulate the world in profound ways. The interplay between abstract mathematics and observable reality is particularly evident in modern physics. Quantum mechanics, once a purely theoretical construct, has provided precise predictions of particle behavior that have been confirmed countless times through experimentation. Schrödinger's wave equation, Heisenberg's uncertainty principle, and Dirac's relativistic equations are not mere symbolic exercises. They capture the intrinsic behavior of the subatomic world. Particles behave in ways that defy everyday intuition, yet mathematics provides a lens through which these behaviors become predictable and comprehensible. This alignment suggests that the universe is deeply structured, operating according to principles that can be expressed and explored through human thought. Mathematics also allows us to anticipate phenomena that have not yet been observed. Einstein's equations of general relativity predicted the bending of light around massive objects and the existence of black holes decades before they were directly observed. The precision with which these predictions were later confirmed demonstrates that abstract mathematical reasoning can uncover truths about the universe that go far beyond human experience. Similarly, in cosmology, mathematical models allow scientists to describe the evolution of the universe, from the Big Bang to the formation of galaxies and stars. Concepts like dark matter and dark energy, though invisible to the eye, are inferred entirely through mathematical relationships and their effects on observable phenomena. The universality of mathematics further underscores its mysterious effectiveness. The same equations that describe microscopic interactions between particles also apply to the dynamics of galaxies billions of light years away. Patterns in nature, symmetry, conservation laws, and invariance manifest across scales, and mathematics captures these patterns with astonishing precision. Human-created concepts like vector calculus, topology, and tensor analysis, once considered abstract exercises, become essential tools for understanding the universe. Our inventions and thought reveal a hidden order that exists independently of us, yet is accessible through reason and observation. This profound effectiveness raises a question that has puzzled thinkers for centuries. Why does mathematics work so well? It is one thing for a tool to approximate reality, as a map approximates a landscape. It is another for abstract concepts, conceived entirely in human minds, to describe natural phenomena with exacting accuracy. Perhaps mathematics is both invented and discovered. We invent the language, the symbols, and the structures, but these inventions align with pre-existing universal patterns. By creating mathematical frameworks, humans access the logic embedded in the cosmos, uncovering truths that are independent of culture, perception, or experience. Ultimately, the extraordinary relationship between mathematics and reality is a testament to both the power of human cognition and the inherent order of the universe. Our minds, through invention and abstraction, have discovered tools that illuminate the laws governing existence itself. Mathematics is not just a language. It is a bridge connecting thought to reality, imagination to observation, and human insight to the deepest structures of the cosmos. In understanding this, we glimpse a universe that is not random or chaotic, but precise, logical, and profoundly elegant, revealing the astonishing capacity of human reason to uncover the truths of existence.